Welcome to AI Paper Slop, where we summarize the latest AI and tech papers. Today, we are jumping straight into a massive new paper called Why Larger Models Learn More: Effects of Capacity, Interference, and Rare Task Retention.
Yeah, this is a huge one.
Right. It's from researchers across Stanford, Harvard's Kepner Institute, MIT, and Anthropic.
And the core insight here really just upends how we usually think about scaling laws.
Definitely.
Like, we all know larger models perform better, right? But this paper proves exactly why from a strictly data-centric optimization perspective.
Which is so needed right now.
It really is. They show that it's not just about sample efficiency. Small models literally physically lack the capacity to retain rare or complex tasks.
Because they just get overridden, right?
Exactly. Frequent tasks constantly overwrite them during gradient descent. But larger models, they allocate so many parameters to the frequent tasks that their gradient updates shrink.
Oh.
Yeah, that reduction in interference acts as a buffer. It basically allows the features of rare tasks to, slowly accumulate and actually stick around.
So if you are an ML engineer listening right now, and you're like tuning your data mixtures or deciding on parameter counts for a pre-training run.
Yeah, this is for you.
This paper explains the brutal reality of why your small model is categorically failing on those weird edge cases, no matter how long you train it.
Right, the training horizon doesn't even matter.
Exactly. So let's unpack the math behind this. Because to understand the mechanics, we first need to look at the divergence between data scaling and model scaling.
Yeah, let's start there.
Because most of us are familiar with the chinchilla scaling laws, right? Where you plot out those predictable loss curves based on balancing parameter count against dataset size.
Right, but the chinchilla formula, it gives an expected loss, but it kind of masks a deeper phenomenon happening under the hood.
How so?
Well, the researchers draw a hard line between what is, quote, learnable via data scaling and what is learnable via model scaling.
Okay, break that down for us.
So if a feature is learnable via data scaling, a small model will eventually catch up to a large model's loss if you just feed it enough data.
It's less sample efficient, but it gets there.
Exactly. It gets there eventually. The trajectory converges.
But the other regime is what really caught my attention here. The learnable via model scaling.
Yeah, that's where the hard floor exists. The paper demonstrates mathematically that for certain parts of a data distribution, a small model given asymptotic resources.
Meaning literally infinite data and compute.
Yes, literally infinite data. It will hit a brick wall. It can never reach the loss of the larger model.
That is wild.
Right. The larger architecture is capturing something fundamental about the task distribution, that infinite data just, it cannot force it into a smaller architecture under standard training dynamics.
Okay, I need to push back on this a little bit just to make sure we are separating the architecture from the training process.
Sure, definitely.
Is this purely an expressivity bottleneck? Let me use an analogy here. Is this like trying to install a 10 gigabyte operating system onto a 5 gigabyte hard drive? Like it just physically cannot fit the information.
That's the most common intuitive assumption. But the paper proves it's actually incorrect.
Wait, really?
Yeah, it is not an expressivity bottleneck. And we know this because you can take these exact same small models and explicitly distill the rare tasks into them.
Oh, I see.
Or you can isolate the rare data and post-train them on it. And when you do that, the small models express the solution perfectly well.
Oh, wow. Okay, so the hard drive is actually big enough to hold the file.
The hard drive is plenty big. The capacity to hold the math is physically there inside the weights.
So what's the actual bottleneck then?
It's entirely about what is learnable under gradient-based optimization, specifically when you're streaming a highly mixed, messy data distribution.
I see.
It's an optimization failure driven by the data mixture itself, not a structural limit of the neural network.
Okay, if the model can hold the data but fails to learn it during a normal run, we really need to look at how it trains.
Exactly.
And to isolate this, the authors didn't just spin up a 4 billion parameter language model right out of the gate.
No, that would be way too chaotic to track.
Right. So they built a highly controlled synthetic environment to watch the gradient updates happen microscopically.
Yeah, they set up a classic multitask learning environment. They used a mixture of k-linear regression tasks and train them simultaneously.
Keeping it simple.
Exactly. By keeping the architecture simple, they could track exactly where every single parameter was being allocated.
And they introduced a crucial metric here, didn't they?
Yeah, they called it feature utility.
Feature utility.
Right. So the neural network allocates its resources based on this utility score, which is driven by two factors.
Okay, what are they?
The frequency of the task in the training data multiplied by the task's complexity.
Let's stop right there and dig into that second factor. Frequency makes sense. It's just how often the model sees the task, right?
Yep, simple probability.
But complexity has a very specific mathematical definition here. It involves the covariance matrix spectrum.
Yeah, it gets a bit dense here.
For those of us who haven't brushed up on our linear algebra recently, what does a slowly decaying spectrum actually look like in the data?
Okay, think of the covariance matrix as a map of how different features in the data relate to each other.
Okay, tracking with you.
When we look at its spectrum, its eigenvalues, we are basically measuring how much unique information is spread across different dimensions.
All right.
If the spectrum decays very quickly, it means a handful of dominant features contain almost all the information needed to solve the task.
So it's like a narrow problem.
Exactly. But if the spectrum decays slowly, the information is smeared out.
Ah, I see.
The model has to track many faint, independent, orthogonal directions to make an accurate prediction.
Which means it's a much wider problem that demands more physical parameters to solve.
You got it.
Okay, so utility equals how often you see it times how wide the problem is.
Right.
And during gradient descent, smaller models are just, well, they're incredibly greedy with how they spend their budget based on that utility, right?
They are mercilessly greedy. The smaller models spend their entire limited width on the high-frequency, low-complexity tasks.
They just grab the easy stuff.
Yep. They max out their parameter budget, grabbing the easy common signals that drop the loss the fastest. And in doing so, they completely ignore the rare and complex tasks.
Let me challenge the finality of that, though.
Sure.
Because if we are just dealing with a greedy optimizer picking the low-hanging fruit first, what happens when all the low-hanging fruit is gone?
That's a great question.
The paper mentions extended horizon experiments. If we train that synthetic model for, say, 1 million steps instead of 100,000 steps, won't the small model eventually look up, see the rare tasks, and start learning them once the common tasks are settled?
You would think so, but the empirical data is definitive on this. It never happens.
Never.
Never. They ran the extended horizon experiments out to 1 million steps, and for the tasks that fell above the small model's capacity threshold, the loss curve remained perfectly flat at the mean predictor baseline.
Wow. It didn't budge.
It never bent downward. Even after 1 million steps of continuous gradient updates, the small model learned absolutely nothing about the rare tasks.
That is wild. It's completely blind.
Totally blind.
Which brings up a massive mechanical question. If the small model never learns the rare task, what is physically happening to its weight matrices when it gets handed a batch of rare data?
Right, because it still has to process it.
Exactly. It computes a forward pass, it calculates a loss, and it backpropagates a gradient. Does it just, drop the math?
No, it does the math. And the crazy thing is, both models actually learn the rare task for a fleeting moment.
Wait, really?
Yeah. To prove this, the researchers designed a matched frequency injection experiment.
Okay, how did that work?
They withheld the rare task entirely for a gap of G steps. Let's say 12,280 steps of nothing but frequent tasks.
Okay, building a baseline.
Right. Then they injected a concentrated batch of the rare task all at once.
So they create this sudden, massive spike of rare data. What happens to the weights?
In that exact moment, if you look at the signal right after the injection, there is a clear spike in performance on the rare task for both models.
Okay.
They call this the gain phase. The small model successfully updates its weights to represent the rare task.
But I'm guessing the small model is about to hit the decay phase. What does that decay look like in terms of parameter updates?
Catastrophic interference in real time.
Oof.
The very moment regular training resumes and the small model sees a batch of frequent tasks, the gradient updates aggressively overwrite those newly adjusted weights.
Just wipes them out.
Completely. The frequent task gradients are so massive that they wash out the delicate structure the rare tasks just built.
Wow.
The rare task signal drops straight back to zero long before the 12,280 step gap is over and the next rare batch arrives.
It's like writing a highly detailed mathematical formula on a whiteboard. And the moment you step away, the next person walks in and aggressively wipes the whole board clean just to write 2 + 2 = 4 in giant letters.
That is a perfect analogy.
Yeah. But why does the large model keep the formula on the board? What's different?
This is the retention phase. And it connects directly back to why capacity matters.
Okay.
The larger model has enough parameters to represent the frequent tasks flawlessly. And because it models them so well, the error rate, the loss for those frequent tasks, approaches zero.
Right, because it already knows 2 plus 2, 4 inside and out.
Exactly. And when the loss is that small, the gradient update calculated during backpropagation is correspondingly tiny.
So the person walking into the room with the frequent task only needs to write a tiny note in the corner of the whiteboard.
Yes.
They don't need to erase the complex formula from the center of the board because they aren't making massive sweeping corrections to the model's weights.
That is the exact mechanism. The frequent task updates become so weak in a large model that they simply lack the magnitude to overwrite the rare task features.
So the rare task just hangs out there.
It easily survives the 1,280-step gap.
Yeah.
And when the next rare batch is finally injected, the large model builds on top of the foundation it already retained.
That makes so much sense.
Yeah, the knowledge slowly accumulates across the gaps.
So tying this back to the ML engineer listening, if you are doing continual learning or you're tweaking your pre-training data mixture, batching your rare tasks closer together might temporarily help a small model hold on to them.
Because you are shrinking that gap.
Right. But ultimately, model width dictates long-term retention. You cannot outprompt or outtune a fundamental lack of width during gradient descent.
Exactly. The capacity isn't just there to hold the rare task. It is there to absorb the constant bombardment of the frequent tasks so they stop destroying your rare task updates.
It really recontextualizes what model parameters are actually doing during training. They're like shock absorbers.
Precisely.
Okay, so the synthetic linear regression models are elegant, the math is clean, and we can, literally watch the matrices update. But language models are notoriously messy.
Very messy.
Do these exact gradient interference dynamics hold up in massive nonlinear transformer architectures?
They do. And that is what elevates this paper from theoretical math to practical reality.
Amazing. How do they test it?
They validated the entire framework by pre-training actual OMO models, ranging from 4 million all the way up to 4 billion parameters.
Wow, real scale.
Yeah, these were trained on up to 210 billion tokens from the DOLMA v1.7 corpus.
But tracking a rare task in natural language data sounds like a nightmare.
Oh, it is.
A concept can appear in thousands of different surface forms. How did the researchers know exactly when a model was processing a specific task?
They actually bypassed the natural messiness using a data injection framework. They borrowed it from memorization literature.
Okay, so they forced the issue.
Exactly. They created entirely novel synthetic tasks that wouldn't exist naturally in the DOLMA corpus, and they injected them at highly controlled frequencies.
What kind of task?
They used a comparison task, which they denote as TCMP, and a modular addition task, TADD.
And how often were they injecting these?
They injected them into the training stream at frequencies ranging from a heavy 1,000 instances per batch all the way down to a vanishingly rare 1 instance every 10 batches.
And when they tracked the performance on those injected tasks across the different OLMO architectures, what happened?
The results perfectly mirrored the toy setup. The 4 billion parameter OLMO successfully learned the rare and complex tasks even when they were injected at those incredibly low frequencies.
And the small ones?
The small OLMO models completely failed to retain them. They flatlined just like the synthetic linear models.
This is the part of the paper that absolutely blew my mind. They didn't just look at the final loss curves and declare victory.
No, they went much deeper.
They went into the hidden layers of the transformer to find the physical learned features. And to do that, they used DAS.
Distributed alignment search? Yeah.
For those who aren't steeped in interpretability research, how does DAS actually prove a model is using a specific feature?
So DAS is a really powerful causal intervention technique. Instead of just observing activations passively, you actively manipulate them.
Okay, so you're messing with the network while it's running.
Right. You take 2 different prompts, say one where the order of the tokens matters for a comparison and one where it doesn't.
Okay.
You run them through the model, and at a specific layer, you swap the intermediate neuron activations between the 2 runs.
Oh, I see.
If swapping that specific bundle of activations causes the model's final output to flip from the right answer to the wrong one,
then you know exactly what those neurons are doing.
Exactly. You have proven causally that those exact neurons are responsible for computing that specific concept.
So it is essentially like swapping out a single wire in an airplane's cockpit while it's flying and seeing if the landing gear stops working.
Yeah, that's a great way to picture it.
If it does, you've causally proven exactly which wire controls the wheels, even in a chaotic system. And using that, they found the exact one-dimensional causal subspace in the first layer of the network that the model used for global token order.
The precision is just remarkable, and they pushed it even further with the modular addition task.
Oh, right, the Fourier modes.
Yes, prior interpretability work has shown that when models learn to do modular addition, they naturally rely on Fourier modes, essentially sine and cosine waves in the residual stream.
Right, because modular arithmetic is inherently circular, like reading a clock. You go past 12 and wrap back around to 1. So it makes sense a neural network would use periodic circular math like sine waves to solve it.
Exactly the reason. So the researchers hunted for these specific Fourier modes across the layers of the different OLMO models.
And what did they find?
They found that the larger models instantiated far more of these task-relevant Fourier features, and they developed them much earlier in the training process.
Because they actually had the space for it.
Exactly. The massive representational capacity of the 4 billion parameter model gave it the width required to physically build the complex periodic mechanisms needed for the task.
Well, the small models simply didn't have the room.
Right.
Finding the physical representations is incredible.
Right.
But did they close the loop? Did they prove that gradient interference, the aggressive erasing of the whiteboard, was the actual cause of the failure in the small OLMO models, just like in the linear regression toy model?
They did. They proved the cause through a highly rigorous gradient analysis.
It must have been tough.
It was. The challenge is figuring out how to measure interference between a highly specific injected task and the general chaotic task of next token prediction across billions of words.
Right, because the gradients are updating everything at once.
Exactly. So they solved this by calculating the cosine similarity between the batch gradients and a task reference direction.
Let's break that down visually for the listener. A gradient is basically a high-dimensional arrow pointing in the direction the model needs to move its weights to get better at whatever it just processed.
Right.
So what is the task reference direction?
The task reference direction is the ideal arrow. It is the direction the weight should move if the model were only trying to learn the rare injected task.
Got it.
The researchers calculated this ideal arrow and then compared it to the actual gradient arrows generated by the standard language modeling tokens, which make up the vast majority of the training batch.
And ideally, you want that cosine similarity to be 0.
Yes.
You want the arrows to be perfectly perpendicular or orthogonal, meaning the standard language modeling updates are moving in a completely different dimension and aren't messing with the rare task updates.
That is the goal. But here is the smoking gun of the paper.
Okay.
In the 20 million parameter model, the gradients from the standard tokens actively interfered with the injected task direction.
Oh, man.
They had a non-zero cosine similarity, and in many cases, it was actually negative.
Negative. That means the standard language modeling updates were actively pointing in the opposite direction.
Yes. They were pushing the weights away from the rare task solution.
So for a small model trying to learn a rare task, a gradient step isn't just a step forward. It is literally 2 steps back. The normal data is actively destroying the rare data.
Actively destroying it, yes. But when they performed the exact same analysis on the 1 billion parameter model,
Let me guess, no interference.
that interference completely vanished. The cosine similarity dropped to 0.
Wow.
The sheer capacity of the 1 billion parameter model provided enough high-dimensional space that the standard language modeling gradients could update the network perfectly orthogonally to the rare task.
So the rare task features were entirely protected from the frequent task updates.
Exactly. They were safe in their own little subspace.
This fundamentally changes how we view parameter scaling. We traditionally think of extra parameters as just adding more knowledge capacity, like, buying a thicker encyclopedia so you can print more pages.
Right.
But this paper proves that extra parameters are actually acting as a structural shock absorber. Larger models learn more, not just because they have more room, but because that massive extra room acts as a buffer against the catastrophic interference generated by high-frequency data.
Yeah, the parameters are an optimization buffer. They soak up the massive, aggressive gradient updates from the frequent tasks so that the delicate, slow accumulating updates from the rare tasks can actually survive from one batch to the next.
It's just so elegant.
It's a purely mechanical, data-centric explanation for why the scaling laws work the way they do.
Which leaves us with a really provocative thought to wrap up on.
Okay, let's hear it.
If the true secret to learning rare edge cases is simply preventing frequent task gradients from overwriting them, Do we actually have to scale dense parameters to achieve this?
Oh, that's the critical question this research opens up. Because if we understand the mechanism of forgetting,
We can engineer around it?
exactly,
Right, like, could we design specific routing architectures, like extreme hypergranular mixture of experts that naturally isolate these gradients into separate subnetworks?
yeah, that's one path.
Or what if we designed entirely new optimizers that artificially enforce orthogonality between high-frequency and low-frequency task gradients during the backpropagation step?
That would be huge.
If we solve the interference problem at the optimizer level, could we theoretically get a 100 million parameter model to retain rare tasks just as efficiently as a 4 billion parameter model?
If the industry can decouple retention from raw, dense parameter count by managing gradient interference directly, the efficiency gains for pre-training and serving models would be staggering.
We wouldn't need to default to massive scale just to protect rare knowledge.
Exactly. It completely changes the roadmap.
It is definitely something to think about the next time you're staring at a loss curve that just refuses to bend, or an edge case your model keeps failing on. Maybe your hard drive is actually big enough.
You're just letting your frequent data reformat the disk every 1,000 steps.
Exactly. Thanks for joining us on this episode of AI Paper Slop. See you next time.